Hi, everyone. Thank you for joining today's PCI-SIG webinar, exploring the technical differences between the PCI Express specification revisions. We'll get started here in just a moment. Hello, everyone. Thanks again for joining today's PCI-SIG panel webinar, exploring the technical differences between the PCI Express specification revisions. I wanted to take a moment here to introduce our panelists today. So our moderator today is Scott Knowlton. He's the Director of Strategy in the IP group with Synopsys. And then our panelists today are Richard Ward, who's Chief Technologist, Data Connectivity with Astera Labs. We have Timothy Pizzaro, Senior Product Manager with Microchip Technology. And Matthew Burns, Technical Marketing Manager for Samtech. So now I'll go ahead and hand it over to Scott to get us started.
Yes, welcome everybody. So what we thought we would do is, for those of you that may not be familiar with PCI Express, we thought we'd give you some of the tenets of why PCI Express is so widely used in the industry. It's very ubiquitous. It works across the complete compute spectrum. You can find PCI Express in PCs, servers, handhelds, workstations, a bit of IoT, and even automotive these days. And one of the key things that have continued to enable PCI Express to move forward and be used for over 20 years is that every approximately 3 years, we double the bandwidth. And we've been able to stay ahead of the demand, of the industry demand for scalable high-performance interconnect and the speeds that are necessary. One of the other things that has kept us at the forefront is being backward compatible. So there is the PCI Express specification. It continues to evolve. But as we've moved forward from the different versions of the specification and the different speeds, we know that that we invest in backwards compatibility. So we know like the latest, greatest device can interop with a prior like PCIe 1.0 device. So they will negotiate and come to the speeds that are necessary to be able to do that backwards compatibility. One of the other benefits of using PCI Express is its low latency. It's a Flit-based encoding in the latest PCI-SIG specification. We keep latency low. It's around 2 nanoseconds. This allows us to meet the performance needs of a load store IO architecture. Fundamentally, we're very power efficient with a low state built into the specification that allows us to proportionally moderate bandwidth usage without interrupting the flow. And the other thing is that we're scalable. You know, I talked about earlier about it being ubiquitous, being in all these different types of applications, but that's because we're scalable. So the needs of, say, a handheld device or a PC could be very different than a server. And so we're able to scale multiple lanes and different data rates in order to get the best possible usage of PCI Express. So we talked about briefly the bandwidth doubling every 3 years. The chart on the left is the usage or the proposal of the spec, and the gray timeline there is basically what we see in the industry as the requirements. So you can see always we stay ahead of what the requirements are, as you know, which becomes key to being able to continue to be adopted. On the right-hand side is the spec revisions and the dates that they were released. in addition to that, you can see the max data rate, the encoding, and the type of signaling that's used. So from the initial spec, we were 2.5 gig with AB 10B encoding and an NRZ format on the line. And our current spec that we're working on with a target release of 2025 is 128 gig using 1B/1B or Flit mode for the encoding. And then, as you can see, we transitioned from NRZ signaling to PAM4 signaling in our PCIe 6 release in 2022, so last year. One of the things that, looking at PCI Express, we've been around, like I said, for over 20 years. And we recently commissioned a research report from ABI Research. And they went through a number of market segments and looking at PCI Express usage. And so looking at that, we see tremendous growth of PCI Express usage in automotive and network market segments for the highest growth rates. And, they're estimating, this report's estimating the CAGRs of 53 and 38% respectively. We see that PCI Express will continue to be used in high performance applications like data centers. It's been ubiquitous there. We're staying ahead of the needs. It'll continue to be used there. We see, the AI industry adoption. Of course, everybody's talking about AI these days, but those were all facilitated designs that started maybe, say, 2015, and incorporated PCIe, and the fruition of all that technology, is being utilized in the latest things that we see publicly about for AI technology. We'll continue to do well on the mobile devices as well. There's a quick pace of innovation there, and there's a number of devices that are used in within the mobile devices, a number of components that use PCIe to interconnect. And as the industry is building up around PCIe 6, we'll consider the recent low power additions or features to continue to help us drive into those functions as well. So with that, we're going to go through I'll ask the panel here some questions and get some perspectives on various things. Welcome to submit your questions here, and as we answer some other ones. So, Matt, why is PCIe 4 technology so prevalent in embedded applications?
Yeah, Scott, that's a great question. That's something I've pondered a lot in my professional, when I'm wearing my Samtech shirt full time, and that really came to fore observationally when I was at a major embedded show in Germany earlier in the year. It seemed like everywhere I went, no matter who the semiconductor supplier was or what the compute engine platform was, PCI 4 was present. And my observation was I kind of came down to two areas. One, PCI, and you mentioned this in your introductory comments, Scott. PCI Express or its predecessor PCI has been around for 20 plus years, and there's a lot of familiarity with the technology, coming out of the x86 environment, the personal computing environment. And when you look at embedded has always been sort of a subset of personal computing, taking x86 architectures and putting into a number of applications. So that's one. There's familiarity with it. x86 continues to be a leading compute engine, compute architecture for embedded applications, and there's just a large install base of customers familiar with PCI Express. Plus, it's easy to use, right? The PCI-SIG's done a really wonderful job, as we've gone from 3 to 4 to 3, 4, 5, 6, et cetera, to make it easy for adoption. Something else too that I think that we're seeing in the industry is, while x86 continues to be a leading compute architecture for embedded, we're also seeing a number of competing solutions when it comes to compute engine architectures. You've got RISC-V coming, you've got FPGAs. those used to be mainly data center. But when you look at entry level or mid level FPGAs or even integrated SoCs, PCI Express 4.0 is either enabled via soft core or hard IP within the silicon. So it's really becoming prevalent. It's not exotic maybe to some new embedded players. And frankly, with some of the value add that the PCIe brings in terms of speed, ease of use, again, ubiquity in terms of compute platforms, it's not a surprise that we continue to see PCI Express 4 being rolled out and adopted in any number of embedded applications. We also see higher performance as you see AI and HPC and machine learning are starting to influence embedded applications as well. So there's always the need for higher performance.
Thanks, Matt. So the PCIe 5 architecture is prevalent in the industry right now. What technical challenges do implementers face in getting these up and running? Richard, you'd like to take that one?
Yeah, I'd love to. And sorry, hello, and thanks for inviting me here today. It's a good one because there are a lot of 5.0 designs completed already, from which we're learning best practices, but there's many more to come. If we look at it from the context of moving from 4 to 5, well, I mean, 5 has still got the 128, 130 encoding. It's still NRZ, and there's many specs that are similar, or the same, such as the lane-to-lane skew. But there's a number of key changes. So the obvious one is that we're doubling the rate from 16 gigatransfers to 32 gigatransfers, which means we're now talking about 1 terabit capacity for a full by 16 BiDi link. The loss budget has increased from 28 dBs to 36 dBs between 4 and 5. But of course, our Nyquist frequency, the highest fundamental frequency inside the data stream, that's increased from 8 gig to 16 gigahertz. And this is really key because it does cause issues, and we need to be a lot more advanced in the way we do analysis. So if we were to take an example like real life channel that was good at 4.0, say an end-to-end loss of 20 dB, that's 20 dB at 8 gig loss, you've got a nice margin to the compliance spec of 8 dB there. Use that same channel though at 5.0, and you're looking at about 38 dB loss at 16 gig. It's not going to work. So it means we've got to implement a number of updates. And two of the key ones are things like using low loss or ultra low loss materials, or taking advantage of retimer solutions. And we're certainly seeing for 5.0 a huge increase in the retimer market. And it's very well documented in the specification, which is great. If you think about the link margin in the loss budget, it also directly affects the recovery and the replay rates. For example, if we're only just meeting the 1E minus 12 BER, well, we've got 1 terabits per second. This implies a bit flip of about every second for a replay at the data link layer. And if we go through the probabilities for recovery, for example, if it was to hit the physical link or the framing errors, this starts to impact system performance. Basically, this means that we feel for the larger systems that we can't really be right on the edge of the spec of the 1E minus 12. You need more link budget to bring that down. Our analysis shows that even adding an extra margin of like 2 to 4 dB extra on the channel link, you can get from something like a 1E minus 12 to a 1E minus 17. So what I'm trying to say is it's clear that we need a lot more analysis for the higher data rate of the 5.0. It's critical to have accurate link simulations using tools such as CSIM, and more focus on the signal integrity, because the PCB and the connector traces and the impedance all matter that much. And then we make the trade-off of low loss materials versus retimers. Also, an extra note is we're seeing much larger systems being developed. Notably AI and machine learning. That's the buzz of everything. But they're a huge component at the moment in the PCIe world. And we're seeing large number of links over both PCBs, connectors, but also custom cables, multiple retimers to enable those reach extensions that they need. One extra thing, I think I'm going over time there. Sorry, Scott. One extra thing I have a bug about here as well is the jitter. So things like the jitter specs of the transmit halved, but you've got things like the ref clock jitter limit went from a 500 femtosecond in 4.0 to a 150 femtosecond in 5. And the reason I feel this is important is the larger systems that we're seeing, again, mainly things like AI, the power has gone up, the systems are getting more complicated. So it's a lot more design effort to keep that jitter of the whole system within the specifications. Okay, thank you.
Thank you, Richard. Timothy, anything to add? Timothy, you are muted.
Oh, there I'm unmuted now. Thank you. Richard did a really excellent job of stating these challenges. I have a little bit to add for the 16 gig Nyquist frequency. And first of all, just to reiterate that signal integrity analysis is essential. And the reason I say that is because in previous generations, you can be a bit sloppy and get away with it. But now you really have to employ this tool. You have to have a signal integrity group do the PCB design. Of course, channel reach is the dominant requirement there because of the loss. If you have a very short reach, then you're not going to have any trouble. But when you have that long reach, you'd have to do that. The thing, or the physics to note is that the wavelength of 16 gig is 12.49 millimeters over copper. And the eighth wavelength is 1.56 millimeters. And it just so happens that an add-in card in the PCB width and the E1.S PCB width is 1.57 millimeters. So you really have an eighth wavelength feature on your design when you go from the top of your board to the bottom of your board. And what that means is you effectively have stubs, and those stubs have a meaningful amount of capacitance or inductance that can affect your transmission. So the feature that you have to be mindful of that. And then the other is that you need to use, of course, microstrip, and which is just good enough at 5.0. And as you migrate to 6, which is you'll likely need to use strip line, but you have to be careful. The other point that I would make is that, so we have the CAM and EDSFF form factors, and they have, some of them have a 2.1 millimeter component height restriction. So that would be the E3.S, E3.L, E1.S, E1.L. And that has a significant impact on your thermal design because you have to fit your component plus any kind of heat sink, and so that is a consideration with the increased power that you get from 4.0. Now, just in conclusion, I have to put in a big plug for the PCI-SIG Developers Conference. So this is an annual event, and all of these problems are addressed in very, very significant technical detail from the people who actually wrote the spec, the people who went through and figured out what that channel margin is. And so you really, I would say, if anybody is considering to do PCIe 5.0 and above, you really must go to the Developers Conference, because that is going to save you a lot of headache. And I'll hand it back.
Yeah. Hey, I know I just want to maybe just add on one more thing that Tim mentioned about the benefits of the PCI-SIG DevCons. I continued to be impressed walking the floor of the DevCons, not only listening to the courses from the technical specialists that Tim mentioned, Scott, but also just the demonstration platforms that are available, both from a compliance standpoint, but also from a testing standpoint. Being able to go to a PCI-SIG DevCon and in essence, rub shoulders with the specialists, I can't agree with Tim more on the point that he made. Interacting with the creators of the technology and those that are dealing with those challenges on a day-to-day basis, you can't recreate that. And as we have the PCI-SIG DevCons coming up in Israel and India over the next couple months, we hope to see several of our listeners at those events.
Yeah, well said. Well said. Well, so Matt, that leads me to your next question, which is, what applications are driving adoption of the PCI 6 architecture?
Anything that needs high performance. That's kind of it in a nutshell, right? And all of us know that we're in a data-centric world, especially coming out of COVID. That more data, more performance, more user, a richer user experience. Sorry, my English is bad today. Is really driving a lot of it. So when you look at it from a vertical standpoint, data center is definitely a key leader there, right? We have when you look at the industry, there's higher performance servers coming out. So the need to link to next generation peripherals, again, just insatiable desire for demand there. And as if someone's attended some of the PCI-SIG DevCons, we can see that a lot of the ecosystem providers are providing next generation hooks to enable PCI-SIG development. Whether that's the IP from the IP providers or test and measurement or whatever the case may be, and it's all focused on designing next generation solutions for data center connectivity. Again, that's from the servers to the communication devices throughout the rest of the system. Richard also alluded to this in his previous answer. We probably have a little bit of euphoria in the industry when it comes to all things artificial intelligence and machine learning, and rightfully so, right? The things that ChatGPT and some of the other AI models that are coming behind it continue to revolutionize the industry, and we're caught off guard. I was driving home this is anecdotal real time. I was driving home from an appointment I had previous to this, since I'm on the East Coast, and there was an advertisement on the radio for an AI-enabled app. If you take a picture of your meal, it can give you a calorie count based on proteins and the like. And if someone uses that or not, I'm not trying to promote the app, but I thought it was ingenious because we couldn't have that conversation 6 to 12 months ago. And to me, it's another example and illustrative of how pervasive AI technology is coming. Not only from a generative standpoint, like so many users in the industry, some users in the content development industry are focused in on, but on real world applications that we haven't even thought about yet. So when you start to, and Richard did a really nice job of talking about this. When you look at the hardware behind AI, the data sets that are behind ChatGPT, I can't say it too quickly. The data sets behind that are enormous. I think when I looked at it, ChatGPT itself is something on the magnitude of about 650 gigabytes. That doesn't sound much because of how big hard drives are, but processing that real time takes a lot of computing power, and then scaling that across an internet connection requires computing power. And PCI Express is one of the enabling technologies to support those solutions. When you start to look at some of the AI system architectures, Tim mentioned earlier about how ChemAIC, PCI Express ChemAIC solutions, and some of the PECFF adding card solutions, they're all based on PCI Express. They leverage a solution that's been available on the market for a number of years, and it continues to get revved, it continues to get updated to meet the demands of next generation solutions like AI. When you start to pull apart these AI systems and do a teardown, it's not one AI chip solution on a ChemAIC. It's typically how many can I get on a single ChemAIC form factor. And what's typically tying those chips together is PCI Express technology. So not only going from card to card, but you're going from chip to chip. And right now, what's driving next generation designs within the industry, within the AI chipset providers, whether that's TPU, GPU, x86, whatever the case may be, is PCI-SIG, soon to be PCI-7. So data centers, artificial intelligence, machine learning are definitely driving the need for PCI-SIG and adoption across the industry. Related to AI is high performance computing or supercomputing. One of the trade shows that PCI-SIG attends is supercomputing in this year, can be in Denver in November. And when you walk around that show year after year, it's to me it's kind of mind blowing the challenges that we face and the mathematical models that are being created by industry or academia or government agencies when it comes to weather prediction and when it comes to stock market or when it comes to genome. That's all based on high performance computing or supercomputing architectures. And again, similar to what you see with personal computing, similar to what you need with AI ML, you're using basically the same IC solutions, or x86, GPU, FPGA, whatever. But how you connect those devices, device at the PCB level, as well as from the shelf at the shelf level, is PCI Express. So you've really got at least 3 areas that are driving the need for PCI Express 6.0. We're starting to see the need for in automotive too, as well as when it comes to autonomous vehicles. Obviously, a lot of that's based on the connectivity between the cars and the cloud. But imagine all that data that's being networked in cars. I've heard some people jokingly say their autonomous vehicles is a smartphone on wheels. Inside of Samtec, we have specialists saying it's a data center on wheels because of the amount of content that's in there. So these and many other high performance solutions are driving demand for PCI 6. They're real world right now. Development is being done in the respective verticals and the respective solution providers. So it's just a matter of time before PCI 6 becomes pervasive in these and other verticals as well.
Which, Matt, I think you had such an extensive answer.
Sorry, I got a little long-winded. I'm so excited about the tech.
Can I just say what he said? So,
well, what I was going to say is, he answered it in such a great way. The next question was, what applications are driving PCIe 7? The next generation that we're doing, and it's all of those things. And PCIe is usually, the interface for networking as well. And so as we move to 800 gig networking or Ethernet, right, networking, we need to be prepared for that next generation, as we, in the data centers, as Matt alluded, there's all this data out there. The sizes are such that we have to move that around in order to be able to act on what it is. So even Matt's, food calorie count example, right? You have to go look that up. You got to look at the data. You have to sort through the different things, and the insatiable appetite to move these big data sets around to figure this kind of stuff out just needs more bandwidth. And so, again, we need to stay ahead. I'll go back to one of the comments I think Matt made on the DevCons and you walking around. 6 is being adopted now. People are building devices to support the industry as it starts to build out its support of PCIe 6. But part of the DevCon, the other thing that we see people showing products, early products on PCIe 6, but we also see, even though PCIe 7 is going to come out in 2025, that's our target for it. We're already seeing technology that's being shown at the DevCons that people can see and interact with folks to show that, hey, this is going to be real. We're already able to deliver technology solutions on top of this, or that are ready for it. And so as we continue to move, we have companies that are making sure that we can implement and produce the specification. The other thing that I'll, just as part of my section here, there was a question that came in is, as we went from NRZ to PAM4, did that mess up the backwards compatibility of PCI Express? And it doesn't. So when we say backwards compatibility, PCIe 7, when we go to the faster speeds, even though there's an encoding change on the PHY, we still backwards compatible all the way down to the 2.5 gig that was introduced with the PCIe 1. So we don't lose any backwards compatibility with the speed change and the signaling change. So, and I think we're going to get back to maybe some of the challenges of that in a little bit here with Matt. But Richard, do you have anything you'd like to add to PCIe 7?
Well, before you do that, I'd just like to comment on something you said, because something that resonated with me is when we're talking about, PCIe 1, 2, 3, 4, 5, really, I see it as one spec. And unless there's a new one out, I see it as 6.1 at the moment. And you can go there and you've got the reference for all the different rates and the requirements. So personally, from different standards organizations, I love the fact that I can go there. And if I want to do a comparison of 3, 4, 5, 6, I can pull up the 6.1 because most of the information is already in there. So now we're at 2,025 pages, I think, at the moment. So it's getting a bit of a beast, but I prefer to have it all in one place like that, because I think that really helps the developers. I just wanted to chip in that point to your, Scott.
Yeah, we're always constantly reminded by our board that it is one specification and it continues to evolve, right, to support the different speeds. So it's a very important point, Richard.
Oh, and did it switch to HTML? When did it switch to HTML? Because that's a lifesaver when you're looking for stuff.
That I can't answer.
Right.
Okay, so kind of in this vein here, what are some of the technical challenges as we shift from NRZ to PAM4 signaling? And Matt, I'm going to throw that your way.
Hey, thanks for that. The short answer is we had to do it to go faster and use the same infrastructure. For someone who's hearing the term NRZ, non-return to zero, and PAM4 pulse amplitude modulation for level, if you're not coming from a signal integrity standpoint, those terms may be imposing from a technical challenge, but they don't need to be. One of the reasons that PCI-SIG was able to make that transition from NRZ encoding to PAM4 encoding is the fact that PAM4 has been used within data center ecosystems for some time. The transition from 28 to 56, when it comes to some of the other protocols that are popular within the data center, and some of the other industry standards that are popular within the data center industry, they kind of took on that challenge and opened the door for adoption from PAM4. So using that really made it easy to move from other interface protocols into what PCI-SIG is doing. So that was really a really good thing. But for those that are learning about those terms for the first time, NRZ basically means that you get with one clock signal, you're able to send two pieces of information on the rising edge and on the falling edge. And when you look at that in the time domain, you're basically sending a 0 at 0 volts, and then you're sending to 1 whatever VCC is, 182533, whatever. With PAM4, you're using pulse amplitude modulation and coding, and sending, instead of 2 voltage levels, 4 voltage levels to 1 clock rate. So what that does is, instead of allowing you to send only 1 bit of information, 0, 1, you can send 2 bits of information. So you go 0, 0, 0, 1, 1, 0, or 1, 1. And when you look at that within the frequency domain, instead of having 0, 0, 1, you've got information at 0, VCC divided by 3, 2 VCC over 3, and then VCC. One of the benefits of the fact is that you can put a lot more information, double the information, on the same Nyquist. So, Tim and Richard did a really nice job kind of encompassing, some of the SI challenges that PCIe implementers face, making the jump from PCI 4 to PCI 5. A lot of those challenges also can be doubled going from PCI 5 to PCI 6 and PCI 6 to PCI 7. However, the PAM4 allows us to use the same Nyquist. So PCI 5, 32 gigatransfers per second, 16 gigahertz Nyquist frequency. Moving up to PCI 6, where you're at 64 gigatransfers per second, PAM4, you're still using the same Nyquist frequency at 16 gigahertz. So when you look at signal integrity, a lot of the signal integrity work is done within the frequency domain. And I don't want to get into a bunch of signal integrity theory here, because you can spend hours talking about that. But there's a lot of technical advantages to using the same Nyquist frequency, but adding more bits basically to your carrier frequency. Some of the benefits of that is not only do you have the doubling of the data rate, but we're also able to keep, relatively, PCI 5 has a total noise channel, I think, of 36 dB. And when you look at PCI 6, it's relatively the same length, I think, but at 32 dB of insertion lossing across the entire channel, die to die. So that's a pretty impressive capability to be able to go from your root complex to your endpoint, double the data rate, but basically keeping the same SI peripherals. In addition to PAM4, which we talked about, For more information on PAM4, there's a great blog that's on the PCI-SIG website that delves into this a little bit more. There's also some videos that we've put up on it on the PCI-SIG from PCI-SIG DevCon, so there's more information available. In addition to that, there's also some forward error correction that's been added to the specifications, which helps to eliminate error within the solution. And then the new Flit-based encoding also helps simplify some of the SI parameters. So it's nice, Richard and Tim talked about the SI challenges you face at the physical layer, PCB, substrate, retimer, et cetera, but PCI-SIG is also trying to handle some of that within the protocol itself with some of the encoding and forward error correction and the like. So it may sound impossible if you've never done it before, but as Tim mentioned, you go to the PCI-SIG DevCons or you interact with the community, and you're literally rubbing elbows with people that have done it. So it is a technical challenge. We're not trying to oversimplify it, but it's been done. There's design support within the PCI-SIG community and the PCI-SIG members. So users or adopters, integrators have the resources to implement the technology.
Thanks, Matt. So
oh, sorry. Could I add a bit to that? That was excellent, Matt. That was a very good explanation. One thing maybe we should add is that when we're going from NRZ to PAM, yes, the Nyquist stays the same, but of course now, because as you said, from 4 levels to 2 levels, or 2 levels to 4 levels, or 1 eye to 3 eyes, we've got that degradation in signal to noise ratio. That's equivalent to a minus 9.5 dB degradation on the signal, which is partly why we had to move that bit error rate specification from a minus 12 to a minus 6 for the first bit error and the requirement for that FEC. So yeah, I love the fact that a lot of the SI stays the same because of the Nyquist, but then let's not forget all that other stuff that comes in, and we're also going from a limiting to more a linear system, and it's been specified very well though. Things like RLM, the quality of the 3 eyes are greater than 0.95. So there's a good old learning curve that we're going to go through with these systems, and I'm looking forward to it. So,
yeah,
Rich,
thanks for clarifying that. I forgot to mention that. Thank you.
Richard, Matt was kind of mentioning Flit mode and such. What new features are enabled by the addition of Flit mode as we've transitioned our encoding?
Lots, right? Yeah, so I think yeah, that's it. That was it. So I think everybody's heard of the flow control unit, which is the Flit mode. It's introduced in 6.0. It's this fixed size of 256 byte block, and I like to think of it as it becomes the underlying like atomic packet of the data flow now. And the reason that we've done that is we want a fixed length because the things like the FEC is more efficient. So basically each Flit block has a self-contained FEC and CRC now. Now you can still have variable length transition layer packets, the TLPs, and that can be a source of confusion as well. So what I like to do is state a simple example. One TLP can span multiple Flits, or one Flit could hold multiple TLPs. So as I repeat, think of it as a low-level data structure block, but we also get a lot of advantages on this because of the way that the format has been modified. We don't need so much of a header an overhead on the header, so we get much higher efficiencies. I'll pick another example of the Flit mode additions. First up, say tags. So why are tags important? Well, because once we get to the higher rates, and certainly you get the longer round trips, again, we're seeing links with multiple retimers in them. If you're on a higher rate and a long round trip time, you could get a bottleneck. The purpose of the tag is to track the requests for the completions. So basically, they're keeping track of everything. Think of it as an address that's flowing through. Now, 4.0 saw an increase to 10 bits, and that gives 768 tag values. 6 extends this again, and as part of the Flit, to 14 bits. So now we've got 15,000. So we've got a substantially higher number of requests that we can use without running out of tags, so we shouldn't hit a bottleneck. One thing I wanted to mention actually about the efficiency increase. I think I mentioned the reformatting because we're removing the framing overhead. And once we add in the efficiency of the lightweight FLEC, the FEC, with its initial correction and the strong CRC, which is further detection, which allows a link level retry. So we're only really looking at 1 to 2 nanoseconds delay by adding that. But the whole thing is becoming a lot more efficient. So I thought I'd pick out a couple of points there. Was that okay, Scott?
No, that's perfect. I'm thinking in the back of my head, as we continue to move different versions and add these features, how easy it is to be backwards compatible through all these different supports of the speeds.
We have to get a bigger spec.
Yeah, we got more pages. But the good thing we're online and just not using paper anymore, right? So Timothy, how does PCIe 7 help foster chiplet-based design flows?
That's a really good question because there's a lot of discussion about how to make chiplets be successful, and you have to have a successful chiplet implementation revolves around a carefully considered partition, and something like a bi-16 lane PCIe 7.0 interface is a very logical chiplet partition that should be considered. And it's the PCIe standard it's ubiquitous, so it gets reused, and the reuse is one of the prime values of chiplets, whether it's reuse as a standard product from a chiplet vendor or reuse from an internal chip development or chiplet development perspective. And it also has a companion UCIe interface for the chiplet to chiplet side. So you have this pairing of a standard to go out to the outside of the chip, onto the PCB, and then you have another complementary standard which goes from chip to chip. And reuse is, I have to reiterate that reuse is a very, very important value proposition for chiplets, and having this partition really makes that reuse compelling. And then finally, it reduces the process dependency because there's a lot of analog, and you don't have the process dependency between analog and digital by taking that PCIe 6.0 interface and sticking it on a chiplet, and then it frees you up to pick. So you can pick a process that's optimized for those frequencies, and then you can have a different process which is optimized for the digital circuitry. So it really is there's a strong case for PCIe 7.0 based chiplets.
Okay, thanks, Timothy. So I'll put this out to all of you. What are some of the challenges integrators face in PCIe technology implementation?
Well, I'll jump in quickly and just to say the challenge is compliance testing, because you've got to go through and demonstrate compliance to all the different rates, so that the whole negotiation, LTSSM, and you have a 2,000-page spec. So there's a lot of features there, but we have a very, very rich ecosystem of IP and component providers that give you those building blocks, and we know that they have passed compliance testing. So that really makes it a lot simpler to pass those compliance requirements.
Yeah, maybe this may be a different viewpoint. I agree with everything that Tim said. There's always signal integrity challenges, right? And there's a good, as we mentioned earlier, when it comes to signal integrity, there's a large ecosystem of support when it comes to using PCIe ChemAIC infrastructure, or adding some of the retimers. from some of the folks on the call here when it comes to extending reach and things like that, right? For integrators or adopters of the technology, doing it for the first time, and all of a sudden they're jumping to PCI 4, PCI 5. There's a large learning curve, but it's not impossible. And it's due to the fact what Tim said is because of so many ecosystem solutions that are available from PCI-SIG members, whether that's IP or reference designs or test and measurement, supports from test and measurement or the interconnect providers in terms of how to design and develop and implement known challenges. I think one of the things that's going to be interesting from an industry standpoint is we've talked about obviously how PCI Express and PCI before it came out of the computing industry, and it computing continues to be a large source of adoption of PCI. But when some of these other applications, AI, ML, supercomputing, automotive, some of the things we talked about earlier, they're going to use new system architectures. It's not going to be a lot of it's PCIe, ChemAIC based, but it's not going to use that same infrastructure. So how are we going to take the SI solutions, the channel loss models, the BER, et cetera, what we talked about? How do you take that and apply it to a new system architecture? We're seeing that in the industry already. It's a small piece of PCIe overall adoption, but it's going to continue to grow. And it's just because in these high growth areas, AI, supercomputing, automotive, system infrastructures for next generation solutions are still on the drawing board. So, ecosystem is always going to be there to support it. But it's going to be interesting to see how the industry adopts with these yet to be determined system architectures as well.
Yeah, maybe I'll chip in. I think part of the strength of PCIe, and also one of the challenges is, I think, as Tim and Matt said, the breadth of the legacy systems that are available. So on the one hand, we've got standards that we must work with so many different root complexes, endpoints, and systems. And then on the other hand, we've also got some very specialized, and we'll throw in AI again, but partly because they're so stressful in terms of the size of them, and let's say they're doing things more custom or possibly on the edge. So yes, you can work through all your compliance, and that's great, but if people are really trying to stretch it to the edge and they really need to, squeeze every last bit of it, then the accuracy of your simulation, as we discussed before, needs to go up a notch to be able to support that. And I mean, I'm very focused on things like the signal integrity and the margins, but the ramifications of that into things like replay and recovery rates and how that affects your performance, it's a very complex system of both from the physical layer all the way up to the data layer down to a recovery rate. So it's the probabilities of each of the layers need to be comprehended for the full system efficiency.
Yeah, all you guys have been talking about, signal integrity and a lot of the stuff on the outside. You guys mentioned IP, and as you look at what it takes to put together the mixed signal portion of the interface and the digital logic behind it to support all the versions and stuff, as a challenge. Like everything else, the clock speeds within the designs just keep going up. The size of the area and the size of the interfaces keep continuing to grow. And so, with all things, it just becomes a part of the big challenge to designing these massive SoCs. And, as Tim talked a little bit about chiplets and stuff, but as we continue to grow in these really big processors and AIs and stuff, it just becomes more important that we're going to be able to bridge and use PCIe to get to these different things. Okay, so let's see here, Richard. So what are the differences in electrical signal reach between PCIe 3 and PCIe 6 specifications?
Well, yeah, okay, that's interesting because if you talk about electrical reach, we're really trying to do the same thing, aren't we? But we're trying to do it faster and more reliably. So if we roll out the specifications again, I think this is very SI based in terms of this conversation. I think that's okay for this. But 3.0 is 8 gig of transfers, Nyquist of 4 gig, compliant channel loss of 22 dB, and a BER 1E minus 12. 6 is 8 times faster. Because of the PAM, we're only 4 times up on the Nyquist, so we're 16 gig. And that's a loss of 32 dB. But I think part of we could drill down into all the numbers, but I think the highlight is that the goal of 3.0, all that time ago, was to try and do things like a server link with 20 inches and 2 connectors. Well, that's not too far off of what we're trying to do now with something running 8 times the speed. And it comes back to the original answer before, what gives? I mean, okay, we've got more powerful SerDes now. We've increased things like the transmit EQs and the receiver when we pull down all the jitter components. So we're using a lot more PHY efficiencies. And one thing I find interesting with the 6.1 spec here, it actually talks about material classes as well, which is not that common for this. And I pulled out a spec here of saying, like, you got to use Meg 6 as good as Meg 6, which is approximately 1 dB per inch over all corners, over temperatures, humidity, everything. So it comes into my first answer, which is you've really got sort of a couple of choices here of how we keep progressing. You've got to go for higher quality simulation work. You've got to have either more expensive ultra low loss materials, or you've got to get those reach extension components into the system, because basically to come back to the original question, what the reach difference is, the reach requirements I see are about the same. And they have been for many years. And if anything, they're getting bigger now, which is where I think with 6, we're going to open up into, possibly different form factors. Possibly, we're certainly going to see optical in 7.0, and I think we're going to see it in 6. So with the disaggregation of systems, we're just going to expand further. So yeah, sorry, a bit of a woolly answer to your what's the reach difference, but the first one is, well, it's about the same, but now it's getting bigger. So. Thanks, Scott.
You mentioned something there. So there was a question that came in on thoughts on optical PCIe. So because you mentioned that, and it's always amazing to me that the death of copper interconnect was predicted. 16 and 32, and etc. And we continue to find ways to make copper work. However, it is clear that we're going to eventually end up going there. And I want to put a plug in here is that there's a new working group within PCI-SIG that's opened up around that. For those of you that have joined and have interest here, as a member of PCI-SIG, we would love for you to contribute your expertise to optical PCIe. Okay.
Could I plug that once more? Because if you were here, so Matt was talking about I think the DevCons coming up. I think Israel and India. If you're at the Santa Clara one, it was just all the rage, all the question. Well, maybe it was in the sessions I was in, but so many questions on optical. What are we going to do? How are we going to do it? Which do we need to change form factors? What are we going to look at? How does it fit with the different standards that are going around at the moment, not mentioning any. So yeah, I think there's a huge wave coming of how we implement those, and I do understand that we're looking at logical changes inside some of the specifications as well to help that optics. And certainly as the systems are growing, we're getting a lot of input of how do we do this? How do we go for 20 meters? Okay. So yeah, thanks, Scott.
Exactly. Okay, so Matt, Timothy, what measures are taken to enable intra-board, inter-shelf, and inter-rack connections? That was intra-rack and inter-rack, but I didn't say that.
Yeah. So Tim, you want to go first? You want me to go first?
Sure. So I would just, what I'd say is that you have to go intra, or I'm going to get this right, intra-rack, then you have a PCIe retimers. And then you also have the higher quality cabling, so Twin-X, and you to extend that reach when you're at least talking at PCIe Gen 5 or Gen 6, then you might want to start considering the optical option where the cost will be justified. And the cabling, as you go to these higher rates, historically the cabling was very flexible and light, and you would compare it to the current band radius of fiber and say, oh geez, fiber is so difficult to work with. But actually, when you get to these higher rates, the cabling becomes more cumbersome than handling the fiber. So that's another option to consider, especially if you go to optics. And this, I think, is why there's such a buzz around the optics. You have a 5 nanosecond per meter latency for each meter of optics, and it's the same for copper, or roughly the same. So you don't have a latency penalty, and then you can go 30 meters or even 100 meters if you wanted to. And there are applications that will tolerate 500, 600, 700 nanoseconds of latency. So it isn't completely out of the possibility. What do you have to add to that, Matt?
No, you stole most of my answer, Tim, but we'll add a little detail. Richard and Tim have kind of talked about this challenge. Scott, is you can't beat Sir Isaac Newton, right? It goes back to physics. The faster your signal is, the faster the Nyquist is. There's a finite length of copper that you can send the signal, unless you add retimers, or you get the signal out of the PCB and get it into a Twin-X cable, which gives you better SI performance. We could spend the entire webinar for an hour talking about the what makes more sense, retimers and or Twin-X, and we're not going to do that here. Or a combination of the two, right? You have active Twin-X solutions. What I find interesting though is, and Richard and Tim already kind of touched on this, is the amount of interest within PCI-SIG communities to start using these other physical layer solutions, right? Anyone that's active within PCI-SIG right now knows that there's ongoing efforts to come up with standardized Twin-X cable solutions to go midboard to backplane, or from midboard to midboard, from board to board, or backplane to backplane within a rack, right? Using off-the-shelf copper solutions, or a combination of Twin-X with retimers that are, let's say, 6 to 9 inches from the PCB, or you're using active cabling, right, to extend the reach. To get to the lengths that, practically speaking, to get to the lengths that that Tim referred to, 20, 30, 100 meters, there's niche solutions that are available from, or vendor-specific solutions that are available right now that do that in the optical domain. I was blown away when we were at PCI-SIG DevCon in Santa Clara at the amount of interest in coming up with a standardized PCIe over fiber solution to answer intra-rack and inter-rack connectivity, because there's demand for it right now. There's solutions out there right now, but they're vendor specific or application specific, or whatever the case may be. For some solutions, it makes sense, but for mass adoption, which is where AI, ML, and supercomputing and data center and these things are going, it's going to get there. So as Richard and Tim, and even you, Scott, you brought this out too, where PCI-SIG is going in terms of creating next generation system architectures within the working groups around copper, and no doubt will be over the next several years around optics. It really gives integrators, adopters, a roadmap, if you will, to support next generation system architectures that these high performance verticals will require.
Okay, so I think we're pretty much here at the end of our webinar for today. I hope all of you enjoyed it, and I'm going to hand it back to Kevin here for some closing comments.
Great. Yeah, I just wanted to thank everyone, thank our panelists especially for sharing their expertise today. It was a great discussion. And I also wanted to thank everyone for attending today's discussion. We'll have an on-demand recording of the webinar available on our Bright Talk channel, also in the PCI-SIG YouTube. And we hope to see you for the next PCI-SIG webinar. Thanks, everyone.
Yeah, and if you're not a member of PCI-SIG, please join now.
Yes, join.
Hey, thank you. Take care.
Bye, everybody.
Thank you.